Today we're going to talk about Adaboost. So before going any further, I want to talk about what this word is and where it comes from. So the ada part comes from adaptive. And then the boost part comes from just boosting, which is a strategy that we're going to use today. I like to think of this as just combining. Right? So as you may recall, we have a lot of things that we've done in the supervised learning space. So supervised learning. We have ID trees, neural nets, SVMs, nearest neighbors, nearest neighbors. And there's a bunch of more things, a bunch of more supervised learning algorithms that we haven't covered that are used in practice. And so what we're going to do today is we're going to take this, put it into our little bag, and we're going to combine these ideas together. And that's what the boosting or the combining part is, okay? And then the adaptive part is just the intuition that we want to make sure that as we choose things that are helping us classify correctly, we want to take a closer look at things we keep getting wrong to try to pick something out that could help us get it right. So, a simple example could be that we have, so let's talk a little bit actually about what classifiers are in terms of math, just some math equations for them that we'll use. So all of these things, we've talked about these, and at the end of the day, once you've made your learning algorithm make one of these things for you, you feed it in a training example, right? So I feed in some x, and I expect to get out some y, okay? So I can give this x to an ID tree on the same data, and it'll give me what it thinks should be the y value. And then I can feed it to a neural net, and it might give me some different idea, right? So these each have different ideas of what the output should be. And even within each category, there are different SVMs within this SVM category and different ID trees, and each of those could give me different ideas of what I would want, okay? And so what we want to do is imagine that we have, let's see, imagine that we have something like this, and we have point A, point B, and a point C. Let's say it just looks like that. All right, and I have some of these. And maybe for one of the SVMs, I'm not going to tell you exactly which line it is, but one of the SVMs, I can represent it with an H. So let's just call it like HSVM. And when I put in X, let's say I put in A, it gives me a plus 1 out. So it's correctly classifying A, right? I might have a different SVM. So let me label these maybe SVM1, SVM2, where I pass in A, and this SVM thinks that A should be a minus, right? And then I might have some neural net where I feed in A, and it might have an idea of what it thinks A should be, right? And then they each have an idea of what B should be and what C should be as well, okay? And so intuitively, well, I guess we could have a situation where we have 3 classifiers. And these could be SVMs or neural nets. I'm not saying at this moment, right? But they take in this point, in all these points. And this one, for A, B, and C, it has some idea of what it thinks each one should be. So maybe the first one thinks that A should be a plus, and B should be a plus, and C should be a plus. So it's getting most things right, but it's getting one thing wrong, right? Maybe this guy thinks that it should be a plus, and a minus, and a minus. And maybe this guy thinks it should be a minus, a plus, and a minus. Okay? So those could be some classifiers that we have in our bag. And the question is, we want to classify this stuff correctly with these things. So maybe we can combine these together. Okay? And so in this example, it's a little easier to see. Just make sure it's showing up here. In this example, it's a little easier than most. And what we can, if you look at it carefully, you can notice that this H1 is actually only getting C wrong. And H2 is only getting B wrong. And H3 is only getting A wrong. Okay? So one way I could combine these is to just say, you know what, I just want you to, for some x, so I'm going to make my combined classifier capital H. For some x, all I'm going to do is I'm just going to say, you know what, I just want H1 of x plus H2 of x plus H3 of x. Okay? And I'm just going to take the sign of this. So all these h's and capital H's too, they always output either a 1, so these things have h's, and h's always output either a +1 or a -1. And we've seen that, right? Like if you're above the threshold for a neural net, you output a +1. If not, you output a 0, but it's like a -1, right? We've seen that for SVMs. If you're on one side of the boundary, you're a +1. If you're on the other side, you're a -1, right? So they all have this sort of form. Same thing here. And so that's the reason I'm using this sign function. The sign function is just going to take whatever number's in here, and just if it's positive, it's going to give you a +1. If it's negative, it's going to give you a -1. And what I've done here is I've added them together, which intuitively is just taking a majority of what they think. And so that's really good because a majority will always get A right, because only one of them gets A wrong, but 2 of them get A right. And a majority get B right, right? These 2 get B right, only one of them gets B wrong. And so if I always take a majority like this, I can classify all the points correctly, even though individually the classifiers I have can't do it correctly. Okay. So just to sum it all up for anyone coming in late, what we're doing is we're taking classifiers from our bag. So we've got all these ID trees and SVMs and neural nets and all that stuff, lots of different forms of them. We have classifiers, so basically, what does this SVM think X should be? It should be a +1 or a -1. And we have a different SVM and a different neural net, and they have different ideas. But none of them do it by themselves. So now boosting is going to combine those together in some way so that we can get the entire space correctly. Okay? Now in this case, I only weighted them each by 1, right? So there's like factors of 1 in front. But I could have factors in front here, and we call those factors the alphas in this for boosting. So there could be alphas in front of here. But we'll talk about those more in a little bit. Okay. So that's one example of how you could combine some classifiers to get a combined classifier, capital H, that gets everything correct. Okay, cool. So let's talk about weak classifiers. So when we talk about the strength of a classifier, we are most interested in, let's see where I'm going to do this here. Okay. When we talk about like the strength or the weakness of a classifier, we're talking about its error rate. And so error rate, you'll see it represented by this big E or sometimes epsilon, depending on which test you see it on. But error rate, intuitively, like on a scale like this. And you could say for one classifier, so for instance this one, what's the error rate? Well, each one of these points might be of different importance, right? A, B, and C, initially maybe we just care about them equally. But boosting, maybe in the future might think, you know what, we've been getting A and B right all the time, but nothing's helping us get C right. So we might weight C more heavily next time so that it picks up something that will help it along with C. Okay? And so these weights right now are all equal, but later on maybe they're not. And so the error rate for this guy, he gets 1 out of the 3 wrong. And right now that they're weighted equally, he has an error rate of 1/3, right? So you can see it like right here, right? Now, if he had gotten 2 things wrong, his error rate would be 2/3, right? And now if these things had weights associated with them that weren't equal, so let's say this thing had 1/4, and this thing had 1/4, and this thing had 1/2. So these weights, I'm just going to call these W's, WA, WB, WC. This is how much we care about getting a point correct. And we'll come back to this idea of how much we care about them. But if we have something like this, we can see that getting C incorrect is actually worth 1/2, not just 1/3. Okay? So we'll just keep that in the backs of our heads that it's not just the number it gets wrong, it depends on how much we care about getting that thing wrong. But intuitively, it's just a sense of like, we got some things wrong, how bad is it? And that's your error rate. Okay? And so what we'd like to do in boosting is always pick the one with the lowest error rate. That seems intuitive enough. As I'm building my classifier, my combined classifier, what I'm going to do is I'm going to keep adding one classifier at a time. I'm always going to add the best one that I've got at the moment. So it's going to start off empty, and then I'm going to add one to it. And then I'm going to see, well, what things did it get wrong? Okay, let's add something to get those things right. Okay, what things are still wrong? Okay, let's add another one to get those right. Okay? And so this thing can be, one thing, or it could be 3 things combined, or as many as you want. But there's an important threshold here at 1/2. And the reason that's important is, imagine I had something all the way over here that was 0.99. It got 99 out of 100 things wrong. So let me ask you this. Let's say you were going to go bet on some horses, and there's 2 horses. And your friend, your buddy, always goes and bets, and he is terrible at betting. In fact, he's really, really bad, so he gets 99 out of 100 races incorrect. Okay? And he predicts for the next race that horse A is going to win. What are you going to do?
Horse B.
Horse B, right? So exactly that same intuition is going to let you know that if you have a really, really bad classifier, you can just negate what it thinks, and you'll get a really, really good classifier. So remember, this is error rate, so we want to be low. Okay? And so 1/2 is kind of a boundary, because anything greater than 1/2, we would just negate it to get a better one. Okay? And so in this region over here, from 0 to 1/2, we call these weak classifiers. And that's a little weird, because intuitively you might think things that get a lot of things wrong would be weak. So why isn't this weak? Well, it's because of that thing where you negate it. Well, then why isn't like the region near 1/2 weak? Well, that's just not what they call it. This is what weak is. Okay, whatever. But intuitively, you could think bad classifiers are really close to 1/2, because negating them doesn't really help you a lot. But good classifiers are either here or here, because if they're there, you can just negate them and bring them over here to a low error. Okay. So we'll keep that in the back of our heads too. But let's just know that definition of weak classifiers, because they say that word a lot. Okay. So now, so we talked about a little bit about the best classifier. And so just to sum it up again, the best one is the one with the lowest error rate at the current step. So the weights are going to change. Those weights I talked about over here are going to change. And we're going to use those weights to calculate the error rate. And the one with the lowest error rate is going to win. And then we're going to keep going another round. So let's talk about exactly what this Adaboost algorithm is. And so just for a second, I'm going to ask you guys to suspend your curiosity of how these equations happened, but they happened, and they're here. So what we're going to do is we're going to weight each point by W. So this A, in this example, would have a WA, and then WE, and a WC. And there's going to be different weights depending on what round we are. So Adaboost operates in rounds. So if we do a round. Okay, and so for a round, I like to write the round number up here in a little like parenthesized subscript. So it's not an exponent, just up there. It's the same notation I use for like training examples, so don't get confused by that. This is for the step, the round number that we're on. So they call them steps, so they put S, but I call them rounds sometimes. Same thing, right? So this is usually what it will look like. Okay. So let's talk a little bit about how these are initialized first, actually. So start the world. So this is step 0. And what we want is for all the weights, for all WI, is going to be equal to 1 over the number of samples. So what this is doing is we're just saying we care about each point equally. So in this example, each one would be 1/3, right? So that's how we start things off. Okay. So that's step 0, and then the rest of that, so that only happens once, but then the rest of this is going to keep looping in these rounds until we get some good result. So let me write, you know what, let me do this. Okay. I'm going to just put arrows for the step numbers in order, and I'm going to write numbers for the important equations that you guys have to know. So I'm going to write the important equations over here. So first equation. the sum of the weights at any step has to be 1. That's just a nice mathematical convenience thing. It's just, we're saying how much we care about each one proportionally, so let's just make them add up to 1. So we have some percentage that we care about for each one. Okay. And then at each step, we can calculate the error rate of some classifier. So each classifier that's in our bag, right? So we might have SVM1, SVM2, and a neural net, and ID tree 8 or something. Each one of these, that's what the C is for, each classifier, is going to have its own error rate. And what we're going to do is we're just going to add up the weights at that step, but only for the I that are misclassified by classifier C. Okay, that's going to give us some error rate. Okay, awesome. And then we have our alphas. And so I didn't put these here, but each one of these has a 1 multiplied by it, and I talked about how they could have a different factor being multiplied. And so we actually have a weighting, how much we care about each classifier's vote, that are called the alphas. And so we have an equation for those. So let me just take a step here to talk a little bit more about this ES and the C subscript that I write. So what I'm saying here is for each classifier at some round, I'm going to do this error. And then the lowest one, I pick that one. And now from now on, I'm only talking about that best classifier, okay? So now I'm giving an alpha to that best classifier, because I'm including it now as part of my set. So I'm giving it some vote, and I'm taking into account its error, okay? So at this point now, we're only talking about the best one. Over here, we're talking about like all of them, and we're picking one of them to be the best one. Okay. And then the final thing is, how do we update our W's, our weights between rounds? So intuitively, what we'd like to do is we'd like to get things that we keep getting wrong, we'd like to increase their weights so that they're more important, so that next time we care more about them, and we're going to include something that will help us get them right. And things that we've been getting right all along, we're going to decrease their weight because we're getting them right all along. Like, let's just stop worrying about them. So that's intuitively what we want. Okay. And so the fourth equation is, how do you get Wi at s plus 1? It's going to be one of two things. So they're going to be 1/2 what the old one was at step S over the minus the error rate, or 1/2 what it used to be over the error rate. And so this one is for misclassified points by classifier chosen for step S, and this one is correctly classified. Yada yada, right? Classifier chosen at step S. Okay. All right. So as you can see, we're using weak classifiers. So we talked about weak classifiers. They always have an error less than 1/2. If you look at these equations, that 1/2 means that these things are going to go up and these things are going to go down in magnitude. Okay? You can see that 1/2 factor there and the 1 minus. You know, they work things out so that these things get increased and these things get decreased. All right. So those are the 4 important equations. So what do we do for boosting? So in a round, we're going to do is we're going to pick the best classifier. And when I write this best with a star, remember I'm always talking about the one with the lowest error rate as computed by this number 2 equation. Okay? Okay? And then we're going to determine its alpha. just how much say it has into the combined classifier. How much do we care about its vote? Then we're going to reweight. So if you guys want, I can put, for this one, what we're going to do is we're going to use equation 2. For this one, we're going to use equation 3. For this one, we're going to use equation 4. Okay. And then the last thing is we're going to stop. Oops, stop. If our combined classifier classifies all correctly, and that's going to be a successful stop. And then we're also going to stop if no more weak classifiers. And that just means we failed. And what that really means is like, well, we got our classifier, our combined classifier, you know, we tuned it and it might have gotten pretty good, but it never got to the point where it got all of our samples correct. Yeah?
So for the second equation, is error calculated by the added up weights of the misclassified?
Yeah. Yeah, so if you know, H4 got examples A, C, and D wrong, I would add up the weights for A, for C, and for D.
Okay.
And that would be the error for that classifier.
Okay.
Do it again for the next classifier, and I just pick the classifier with the lowest one. That's it. And we'll go through an example, so you'll see this like really being worked out. Okay, cool. Okay. So I'm just gonna say a little bit about why the hell we're doing this. Like this seems like it just kind of came out of nowhere. Like intuitively kind of makes sense, but is this really gonna work out? Like, is more rounds and more rounds, like maybe you could think, if we keep decreasing the weights of the things we keep getting right, maybe later on they'll be so weighted so low that we'll start getting them wrong again. And then that we're not going anywhere, we're kind of just going in circles. So is that really gonna work out? And so what I'd say to that is you're not expected to know that in 034, you're supposed to just trust us that it works. But I'll talk just a little bit about the fact that if this is the error for our combined classifier h of x, and this is the number of rounds, or s's, or steps, there's actually some math about why we chose to update alphas in this weird way and why we chose to update w's in that weird way. Like, why did we choose that? It turns out that by choosing those, we can bound the error over the number of steps by some sort of like exponential decay function. So the actual error you'll see is like, oh, our classifier is really bad, it gets a lot of things wrong. Oh, now it's really good, now it's kind of bad again. Now it's getting better, oh, even better, but it stays within this bound. So the more steps you do, you're gonna bound it closer and closer to an error of 0, okay? And that's just how it works out with the math. So I don't expect you guys to just believe that, like, you know, without further looking at it. But that's all we expect out of you guys for 034, because this stuff is a little complicated and not really worth our time. Okay, cool. Now these equations actually came out of other ones. I'll talk about this just really quickly too. These weights actually had alpha terms in them and stuff, but we like kind of massaged the equations a little bit and got them to look like this, because that's a lot easier to compute by hand. The other things were like e raised to the minus alpha, and we don't want you guys to do that on a test, so this is like an easier way of computing w's. But there's actually an even easier way of computing w's, which I'll talk about when we do the example. And so you could do this, and this is always right. There's a super shortcut that helps you do it even better. Okay, cool. So does anyone have any conceptual questions about like why we care about this? Why is this maybe a good idea or anything like that before we move on to an example? All right. So let's do an example. Okay. So I'm actually going to do, let's see. I'd like to keep these equations up there, but I wrote them kind of giant. Okay. I think I'm just going to work over here. Okay, cool. So if you can't see from over there, make sure you move over here. All right, so this is from quiz 4, 2012. And so in this problem, they give us, as always, our favorite x1, x2 grid. 1, 2, 3, 4, 5, 6. And they give us they give us a plus and a plus and a minus and a plus. Okay. Awesome. So they say in this problem you'll use boosting to construct a classifier for the following training set. This thing. Okay. And so they give us the bag, they fill the bag up for us and tell us which things we're allowed to use. So we're allowed to use things of the form x less than or equal to t or x greater than or equal to t. So something that in the plane looks like this, or something that in the plane looks like that. Okay. So those are the two things we're allowed to use. And now the h function that comes out of these things is I could have, so h of x is just going to be a 1 minus 1 if x1 is less than or equal to t else, right? And this one's just going to be greater than or equal to t or else. Okay? Cool. And so now they give us, I'm going to erase this. And I've got it in my head, so as long as you guys have it in your notes too, we're good. So, okay. So they say, for the following set of 6 classifiers, they label these things A, B, C, D, E. Okay. So the following set of 6 classifiers list all the training points A, B, C, D, E that each misclassifies. If a misclassifier misclassifies no points, write none instead. Okay. It's a mouthful, so let's do this. So these are the ones that they gave us. They say analyze these 6 classifiers. Okay. And now for each one, let's just list the things that it misclassifies. Okay. So just so you guys can see, A and D are both on this 1, and B and E are both on this 5, and C is on a 3. Okay. So what do you guys think? For x less than or equal to 2, what things does it misclassify? B and E? Yeah, so it's going to be a line right here, shading on that side. So it gets A right and D right, it gets C right, but it gets B and E incorrect. Do the same thing for 4, and we're going to get C, B, and E. We can do the same thing for 6 and just get C. And now for this one, we can look at greater than 2, right? So it's going to get B and E right, but it's going to get A, C, and D wrong. And then for 4, we're just going to get A and D wrong. And for greater than 4, we're going to get A, B, D, or E wrong. Okay.
The last one greater than 6.
Yes. Thank you. Okay. Cool. So that's 5 points. Awesome. You guys didn't even know anything about boosting when you get those, so that's great. So now, they ask us, which of the 6 classifiers from this list will surely never have the least error? In other words, boosting will never pick some of these. For some reason, there's at least one of these that boosting won't pick ever. This one? So what do you think? Not that one. So what do you guys think? So let me put it a different way. We're always going to pick the ones with the least error. Okay? Remember, the error is calculated by summing up the weights of the things you got wrong. These are the things they got wrong. The weights are always positive. So this thing, let's compare these two. This one is always greater than this one, the error rate. Because this one's going to have the weight for B and the weight for E. This is going to have the weight for B and the weight for E, but it's also going to have the next weight for C. So this one's always going to have a higher error rate than this one. Okay? So we're not really going to ever pick this one. Now you could say, but maybe if you flipped it, like we said, around the 1/2, if you brought it over by negating it, it could be pretty good. And so you're right, and maybe what you'd want to do is, you could argue maybe we want to include a 7 classifier, which is the inverse of this guy. It turns out this is already the inverse of that guy. So we already have him included, so it's no foul. We can just cross this guy out and say we'll never pick him. Okay? Similarly here, we have a C included, and this one just has A and D, so this one's always going to have a higher error rate, so we're never going to really pick this one. Anytime this guy would have been a good choice, this guy will be a better choice, right? And then same thing here. This guy is worse than, we could analyze it with this or with this guy. This guy's just really terrible, so we're just going to get rid of him, okay? And so now we have these 3 candidates. Awesome. So that's another 5 points. Okay, and now comes the meat of the problem. Get rid of this. So this next part's worth 24 points. So this is like really what we want you guys to know for the quiz. Okay, so they say perform 3 iterations of boosting using the training points A, B, C, D, E, and the 6 classifiers from part A. So these 6, right? But we know we'll just never pick these, but they're there. And they order them. They say if there's any tie breaks at any point, pick the one in this order, like going this way. Right? So this one comes before this one, and this one comes before this one, right? Just that way. Okay. And then they say fill out this table. So let me take a second to write down the table. So we've got 3 rounds of boosting. Okay. And then what are the things we need to keep track of are the weight of A, the weight of B, the weight of C, the weight of D, the weight of E. Then we need to pick our classifier and list its error, and then the alpha for the thing we picked. Okay. All right, so let's start. So they start with round 1 instead of round 0. Sometimes they 1 or 0. So when I said start the world over here at round step 0, this is really step 1, I guess, for this problem, because that's where we're starting. All right, so what do you guys think? How can we start filling this out? Yeah, so we're going to weight each of these equally, given our start the world order. So that's going to be 1/5, 1/5, 1/5, 1/5, 1/5. Makes sense? So far, we care about them all the same. Okay. And now we can ask, so when it comes down to them all being the same, there's a shortcut to picking the best classifier. You just pick the one that misclassifies the least number of points. You don't really have to take into account the weights because they're all equal. Right? So we could take that little shortcut, but let's just be really rigorous about it, just so we see what's going on. So if we look at A, for instance, are we going to pick, sorry, not A, are we going to pick this guy? So this guy gets B and E incorrect. So we look at the weights for B and E, we add them up, and we get 2/5, right? So this guy has an error rate of 2/5. We're going to skip this guy because he's going to have a higher error rate. Okay, what about this? This guy, we just add a, well, but just the 1/5. So that guy has an error rate of 1/5. And we look at AD. AD has 2/5. And so the lowest one was this classifier. And so they want us to write down the one we picked, which was this one. The error rate for it, which we said was just 1/5, because we just added up the one term right here. And the alpha for it. And so now I'm going to use that equation. Where is it? This one. So it's 1/2 ln, and then you do 1 minus 1/5, which is 4/5, over 1/5, which you just get 4 in the inside of that. Okay, awesome. That's pretty straightforward. right now, this step that we're about to do right now with the reweighting is where if you know this part, you'll get everything right, and if you get this part wrong, you'll get the rest of the problem wrong. So this part's like the most important, okay, in my opinion. So now let's do it with that equation that I erased so kindly, with the reweighting equation, and see what we get, and then I'll show you guys the trick for doing it even faster and better. So I'm just going to rewrite the equation for myself. Wi s plus I s plus 1, and it's going to be equal to 1/2 Wi s over 1 minus e to the s, or 1/2 Wi s. Okay. So this is for things we got right, and this is for things we got wrong. So let's look at A, for instance. So A, we're going to take 1/5. We're gonna put it over the error rate, which was 1/5. That becomes 4/5 on the bottom. So 1/5 over 4/5, and we take half of that. So I think we end up getting 1/8 if my math checks out, which I think it does. Okay, cool. And so we can do similarly. B is going to be the same thing. I mean, we still use this equation because we classified B correctly with our classifier. The error rate's still what it is. All's well, so we get this. Same thing for D, same thing for E. Okay. Now we don't even really have to use this one if we don't want, because we can use equation 1 to say, well, the sum of them has to be equal to 1. So then this middle guy has to make them add to 1. So this is 4/8, right? 1/2. But we could do the equation, so let's just do the equation really quick. So 1/5, but it's over just 1/5, right? So that's just 1, and then there's a half. Yeah, 1/2. So this is 4/8. Just going to keep it in eighths, just to keep everything nice and consistent. Okay. And now I'm going to show you guys the trick we could have used. So there is some trick equation. This is like what I like to call the trick equation, which is I'm going to list it as equations 5 and 6. These are tricks. And it's that the sum of the ones we got right have to be 1/2, and the sum of the things we got wrong has to also be 1/2. Now this falls out of combining these equations together, and the equations that derive these, we can get these, so we can like prove it. But intuitively speaking, what this is saying is, imagine what would happen if we stopped caring too much about the things we got right, or we cared too much about the things we got wrong. So this kind of helps us balance that out. So we care as much about the things we got wrong as the things we got right. But we'd like to make the things we get wrong smaller and smaller, like just smaller and smaller number of points. But we want to weigh each of those up more. And so they should just add up to 1/2. Okay. So we can use that trick because we know that this thing, this 1c, has to account for that whole 1/2 of the things we got wrong. Also, it has to become 1/2. It's the only way we can do that. And then the other guys have to maintain their ratios. So this guy has a ratio of 1 to 1. 1 to 1, right? These guys are all like equal. So they have to still all be equal, but they have to add up to 1/2. So 1/8. And now we don't have to use those equations over here. We can kind of do it a lot faster. All right? So we're going to use that trick for the next time we do it. But now which classifier does the best now? So now the weights have changed. So this is no longer going to be the best one. Okay? So which classifier does the best on those points? So we've got some of these crossed out, right? So this one, or this one? Well, let's look at the one we just had real quick. We got C wrong. So it's going to get automatically at least 1/2 as its error rate. That's like the worst we can do for weak classifiers. So this one's probably not the best one. How about this one? B and E, that gives us an error rate of 1/4 if we add them up. And then this one gets A and D, which is also 1/4 if we add them up. So there's a tie. They told us to break ties by going in this order. And so this one comes first. So we're going to pick that one. Okay. And the error rate, as we said, was just 1/4. Right? Just 1/8 plus 1/8 for B and E. And then the alpha is just going to be 1/2 ln of 1 minus this thing over that thing. I think we get a 3. All right. So now let's do another round of boosting. But now we can use our super awesome half trick to do it faster. So what are the things we got wrong? We got B and E wrong. Okay. So these things have to keep their ratios. Well, they're equal, so they better still be equal, right? If this one was like twice the size of this one, we'd still have to keep it twice the size of that one, right? We'd multiply by the same constant. And we have to make them add up to 1/2. That's easy, they're each a fourth, right? And now these guys have to add up to 1/2 because we got them right. But we have to keep the ratios of 1, 4, 1. So 1 plus 4 plus 1 adds up to 6. So I'll double that to make a nice fraction, 12. So this is 1/12. This is 4/12. This is 1/12. In fact, I'll rewrite this as 3/12 just to keep everything in 12s. Done. Okay, so we don't have to use those equations over there. Okay, cool. And now we can ask again, which is the best classifier? And so we can look again. And we can say, okay, BE. BE. And you'll notice the one that we just picked on the round before is always going to have 1/2 of it as its error rate next. Right? 1/2. And that's just because the things we got wrong in the previous step have to add up to 1/2. So if we pick the same one again, we'll get the same things wrong. They'll add up to 1/2. Okay, so we're not going to pick this guy because that's 1/2, unless everything else is really terrible too. Okay, what about just getting C wrong? Okay, so that's a third. Okay, what about getting A and D wrong? A and D is just a 1/6. So that's the best classifier. So let's pick it. So that's x greater than or equal to 4. That's 1/6, right? And I think this turns out to be 1/2 ln of 5. Okay. And so now you can ask, okay, we did all that. That was just like random computation for like the test, but how would I actually use this stuff? So these things are useful because they let us figure out this. If you could just figure out this like right off the bat, you wouldn't need all these W's and stuff. You would just say, okay, my classifier is my big H that I pick is going to be my alpha. So I'm going to call this is going to be H1, this is going to be alpha 1, this is going to be H2, alpha 2, this is going to be H3, alpha 3. Then all I have to do is say, I'm just going to take the sign of alpha 1, H1 of x, plus alpha 2, H2 of x, plus alpha 3, H3 of x. That's it. So this is what we wanted in the first place. So if you could just get the alphas like without doing these W's, you would. But you can't. So you have to go through this stuff so you can figure out this stuff. So you can figure out which one you should have picked. Okay. Cool. So we did 3 rounds of boosting. So hopefully we've improved it as we gone along. And so now we can ask, how well does it do? Does it classify things well or not well? So we can actually do that exercise really quick. So actually they ask you, consider the total classifier H, which you produce after 3 rounds of boosting. List all the training points A, B, C, D, E, which H misclassifies. If there are none, write none instead. Show your partial work if you want extra credit. Okay. So I'm just going to get rid of our super equations here because I'm done with this problem. Go through these. Okay. And so they give you some stuff. So they give you that the ln of 1 is approximately 0. Ln of 2 is approximately 2 seconds. Ln of 3 is approximately 1. Ln of 4 is approximately 6/5. And ln of 5 is approximately 8/5. Okay. And so let's consider point A. Let's see if it gets point A right. So let me erase this stuff too. So let's plug in point A. So it's going to be 1, 5, right? That's where A is. But this classifier, it kind of only cares about like this coordinate, right? It's just a line that's like perpendicular, and it's whether you're on the left or the right. So we're just really caring about if it's on the left of 2 or the right of 2 or the left of 4 or the right of 4. So let's just look at it really quick. We have, so let's do the alpha first. So 1/2 ln of 4. So 1/2 ln of 4 is 7/5, so 1/2 of it is 7/10 times, what does the classifier think it should be? So x less than or equal to 6. Is it less than or equal to 6? It is, so it thinks it should be a plus. So it thinks, I cast my vote as a +1. Okay? Okay, next classifier. So he has an alpha 1/2 ln of 3. And so ln of 3 is 1, so 1/2 of that is 1/2 times it's what it thinks it should be. And so what do you think it should be? Less than or equal to 2? We are, so it thinks it should be a +1. And the last guy has 1/2 ln of 5. Ln of 5 is 8/5, so half of it is 8/10. I'm just going to write this as 5/10 just to keep everything in tenths. And what does it think it should be? Greater than or equal to 4? It's not, so it thinks it should be a minus. Okay? And so now we add these all up, and so we get 7/10 plus 5/10, we get 12 minus 8, so we get 4/10, right? We're taking the sign of this thing, right? Here's the sign. It's a positive number, so we're just going to get +1, which is correct, right? Because A is a plus, and we got +1. Right? We can do the same sort of thing for A, B, C, and D, and E, and you'll actually find that it classifies all the points correctly. And so you would show that in your partial credit by writing these things out. And then you would say none of the points get misclassified incorrectly, or misclassified. Yeah, right. Awesome. Okay, cool. So we've actually made a perfect classifier from 3. Now, it's not like guaranteed that it was going to take us 3. It could have taken us 8 steps. In this case, we just happened to get lucky on 3. But there's actually an important fact that you guys should know, which is that you can make a perfect one if you have classifiers with non-overlapping errors. Okay? Now, I just want to be really clear on this. You can also make perfect ones when this isn't true. Okay? So this is it's not an if and only if. But if you do have non-overlapping errors, you know you can make a perfect one. If you don't, it's unclear. Like you might be able to, you might not be able to. Okay? And so a great example of this was actually the first example I gave with the A, B, and C. Remember, each one only got one thing wrong, and no two got the same thing wrong. So those 3 things each had non-overlapping errors. So one thing got A correctly and B correctly, but got C wrong, and the next thing got A correctly and B wrong, C correctly, and the last guy got A, B, and C right, but A wrong. So you can see the errors don't overlap, and so this actually, we know right off the bat that we can make a perfect classifier with those 3 classifiers with some weighting. So we can just prove it just by saying that. Now, if this wasn't the case and we had something like this, we can't say that, but we still might be able to make something that works, that is perfect. Okay. Yeah.
So for each round, would we do the alpha calculation, or would we do the big H of x calculation with the alphas we have theoretically?
Yeah. So if they didn't ask you to, they told you to do 3 rounds of it no matter what. If you're really doing the algorithm, which is supposed to stop depending on if you've classified everything correctly or not, yeah, the computer is supposed to do that calculation on every round. And then if it gets nothing wrong, it just stops.
Okay, so for most of the time they'll tell us how many rounds to do it?
I think every single test question I've seen tells you how many rounds to do. So I think you should be okay with that. All right. Cool. Let's see. So did that. Did the tricks. Cool. I think that's all. Tests are at Winston's office, so you can go at any TA's office hours to pick them up.